will now explain a bit the three kinds of heat exchangers we have developed. So we have two kinds of heat pumps, and these heat pumps need innovative heat exchangers. And I'm going to show you this kind of three innovations. One, it's focused on the ice slurry approach. And I just want to show quickly, this is a traditional ice storage, what is called ice on coil. This is something that is being constructed. At the end, tubes are everywhere in the storage. So this has a high cost of construction and material, and that's why we are aiming to delete and eliminate all these heat exchangers. So an ice slurry system is a vessel like this one without anything in. And this reduces the cost dramatically on this part, which is a key aspect on this kind of system. And this has the benefit also that can be used for refrigeration applications. We are applying this to heating, but it has a higher potential even for cooling applications. So we said, okay, we would like to use a slurry, and what exists today as a slurry is what is called an ice scraper. So basically you have a very cold surface where ice is built, and then there is a rotating machine that scrapes ice from the surface and produces a slurry. But these things are very expensive, need a lot of maintenance costs, and therefore they are not really deployed in Europe, despite the fact that they exist commercially. So what we propose instead is what is called a supercooling concept. And supercooling is a simple idea, difficult to do in practice, which is we take water, we cool it down below the melting point of water, and at some point we cool it further until we disturb water in what we call a crystallizer, and then ice slurry is produced, the latent heat is released, and then we have this slurry flow. And the difference between the melting point and the actual crystallization point is what we call the supercooling degree, and the higher the supercooling degree, the higher the probability of freezing. So in order to achieve a stable and safe supercooling degree, what we did is we developed isophobic coatings, so coatings that are able to delay the formation of ice, not eliminate it, but delay it. And these coatings have been applied in brazed heat exchangers on commercially available heat exchangers, and we have tested this in the lab. Now, I don't have time to go into the details of these results. I will just focus on, this is a reference heat exchanger, so this is a commercial heat exchanger without any treatment. And let's now just look at, for example, HOIS 2. This is an hybrid organic, inorganic, silane salt gel coating developed by DTI. And this coating is able to reduce the outlet temperature of the supercooler by 40%. It means that in average, this is the different results on the experiments. We did several testings. And on average, we were able to achieve -4 degrees water in the outlet of the heat exchanger in liquid form. Second heat exchanger we developed was a three-parted gas cooler. That's necessary for CO2 applications with a transcritical cycle. For those that are not on the CO2 side, I would say a gas cooler is an equivalent of a condenser. The difference is that in transcritical CO2 cycles, the CO2 is not condensing, but it's having a large delta T into the gas cooler. And this means it's very good for domestic hot water applications where you can have water heated up from 10 to 60 degrees, but it's not good for space heating. And then NTNU developed this heat exchanger, a three-parted gas cooler that is able to follow CO2 very well with preheating domestic hot water, providing a space heating, and providing reheating of domestic hot water. So this increased efficiency significantly when operated in parallel, plus can provide space heating demands. And what existed before 3HP was this, also at NTNU. It is a lab thing, custom made, and now they made it using plate brazed heat exchangers, and they were able to reduce the weight by 80% and the area significantly. So the third heat exchanger is what is used in this dual sourcing. And the main innovation here, I mean, this is the kind of the heat exchanger, which is basically a coaxial tube, where in the annulus there is the refrigerant, inside it's the brine, and outside there are fins, and there is air blowing on it. And the main innovation is that there is a direct exchange between the heat transfer fluids and the refrigerant, and that's why this heat exchanger is quite efficient. And so Tecnalia developed this. This is one of the prototypes, and they developed two kind of prototypes with quite an improvement from the first to the second. The second one has these corrugated things inside the tube to increase heat transfer coefficient. And they were able, with their measures, to reduce the internal volume of the heat exchanger from 15 liters to 5.5. This reduced the surface area from 112 to 54, and of course then the refrigerant charge was reduced significantly. Thank you very much.